Hello and welcome to another Deep Dive Explainer. I am absolutely thrilled to have you here today. Listen, if you're currently preparing to sit for the Cambridge Computer Science exams, and we're talking about syllabus codes 0417, 0478, 2210, or even the Advanced AS and A-Level 9618, then you know exactly how incredibly demanding these papers can be. They don't just test what you know, they test how you think. Okay, let's dive right into this. I want you to imagine, just for a second, that you are a paleontologist. What exactly does a paleontologist do? Well, they definitely don't just drive a massive, heavy bulldozer into a fragile dig site, scoop up a giant pile of dirt, dump it all onto a laboratory table, and just kind of hope there's a valuable dinosaur bone hidden in there somewhere. No way. They are meticulous. They are precise. They use incredibly small brushes. They identify the exact specific layer of ancient rock they need to look at, and they carefully, intentionally excavate the specific fossil they are searching for. Now, I want you to think about your own exam strategy right now. I look at so many past papers, and I see so many incredibly smart students act exactly like that bulldozer. Let's call one of our hypothetical students Alex. Alex is the bulldozer. Alex walks into the exam hall, flips open the paper, sees a question about binary addition and overflow, absolutely panics, and just dumps every single raw fact they have ever memorized about binary data onto the page. There's no analysis, there's no structure, there's no linking to the scenario. It is literally just a bulldozer of raw data. And then, on the flip side, we have our second student, Sam. Sam is the rusher. Sam is always watching the clock, always trying to finish early. Sam reads a familiar keyword in the prompt, completely misses the crucial command words, the words like explain or evaluate or justify, and ends up writing a totally brilliantly written, perfectly accurate answer to a completely different question. Both Alex and Sam studied hard. Both of them know the material. But both of them are going to lose massive, massive points. Today, we are going to transform you from the bulldozer into the paleontologist. We are going straight into the specific fossil layers of your exam questions to meticulously reconstruct the exact, perfect answer that Cambridge examiners are actually looking for. So pose this absolutely critical question to yourself for a second. Why do perfectly memorized facts score 0 marks? Seriously, think about it. The uncomfortable truth all comes down to Cambridge computer science assessment objectives. You can have the entire textbook memorized word for word. You could literally recite the definition of a MAC address backwards. But if you do not answer the specific, targeted demand of the command word in the question, you get a 0. Zip. Nothing. Cambridge examiners aren't just testing to see if you possess a dictionary of computer science terms floating around in your brain. They are testing if you can strategically apply those terms to solve highly specific digital problems. For example, let's say a 4-mark question asks you to explain the consequence of an overflow error in an 8-bit register. And let's say you just write down the textbook definition of binary code, and then you do a flawless, mathematically perfect calculation of an 8-bit addition. Well, you get 0 marks. Why? Because you missed the core of the question. You recognized the familiar term binary addition, and you essentially answered a completely different question from the one that was actually set on the paper. You acted exactly like Alex the bulldozer. We need to completely stop rewarding ourselves just for remembering facts during our revision, and we need to start aggressively training ourselves to decode exactly what the examiner is asking for. All right, so here is our map of the dig site for today's explainer. First, we are going to start by actively avoiding the bulldozer trap. Second, we will learn how to strategically dig through the 3 layers of knowledge. Third, we'll tackle the absolutely critical mark-defining difference between description and explanation. Fourth, we'll explore the power of context in your answers. And finally, we will finish up with the 4-question mastery check to lock it all in. Let's get moving. Section 1. The bulldozer trap. This is the part of the explainer where we diagnose exactly where so many well-prepared students lose marks right out of the gate. We're talking about falling into the same trap as our friend Sam, who skips the command word entirely and just starts writing furiously based on a single keyword. Look at this quote directly from the examiner reports. Many avoidable losses of marks happen because candidates recognize a familiar word and then answer a different question from the one that was actually set. Let that really sink in for a moment. It brilliantly illustrates the absolute crux of the issue. Let's say the exam question is specifically about binary addition and overflow. The familiar word that jumps off the page is overflow. Sam sees the word overflow, and his brain immediately, instinctively jumps to storage. He starts writing a massive, incredibly detailed paragraph about how a secondary storage hard drive gets full, how solid-state memory runs out, and how the user needs to delete video files to make room. But that is completely fundamentally wrong in this specific context. Binary overflow in data representation happens when the mathematical result of an addition requires a ninth bit, but the computer system's hardware register is structurally only designed to hold 8 bits. The extra bit literally falls off the end, the data becomes hopelessly corrupted, and the computer makes a catastrophic mathematical error. It has absolutely nothing, zero, to do with your hard drive being full. But because Sam fixated on a surface feature, a familiar everyday word, he completely ignored the deeper digital problem-solving sequence being tested. Now, before we continue and look at how the examiners spot these errors, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's look at the examiner red flags on this slide. These are the exact, specific things that make a Cambridge examiner pull out their red pen and instantly deny you marks. Vague wording. Confusion between superficially similar terms, like confusing primary memory with secondary storage, or confusing the physical infrastructure of the internet with the software protocols of the World Wide Web. Missing critical steps in a logical process. I want to do a quick interactive workshop with you right now. I call this Challenge 1, Find the Flaw. I'm going to put a mental 60-second timer on the clock, and I'm going to read you a sample paragraph written by our bulldozer student, Alex, about binary addition. Listen incredibly closely to my words and try to spot the red flag from this list on the screen. Ready? The clock is ticking. Alex writes, binary addition is when you add ones and zeros. An overflow error is bad because it causes a problem. This is a disadvantage of 8-bit systems. Time's up. Which of the red flags did Alex just hit? I'll give you a second to think. If you said vague wording and stating an advantage or disadvantage without a reason, you are absolutely 100% correct. Think about it. Alex literally says it's bad because it causes a problem. What problem? How exactly does it happen? This is exactly where error-aware revision is far, far more useful than just passively memorizing correct facts. You need to know how to spot a fundamentally weak answer so you don't accidentally write one yourself under the pressure of the exam hall. Moving right along to section 2, digging through 3 layers. This section right here is exactly how you transition from just recognizing a vague concept on a page to actually scoring maximum points for it. Listen carefully, because this strategy is your golden ticket. The ideal, perfect revision walkthrough moves purposefully through 3 distinct layers of understanding. Step 1 is the simple explanation. This is everyday, plain English language. My rule of thumb is, if you can't explain binary overflow to your grandmother, you don't really get it yet. In everyday language, it sounds like this. We have a small cardboard box that only holds exactly 8 items. We stubbornly tried to shove 9 items in. The box broke. Simple, easy to grasp. Step 2 is the technical explanation. This is where you level up and intentionally inject the correct Cambridge computer science subject vocabulary. An 8-bit register can hold a maximum denary value of 255, which is represented as 8 ones in binary. If we mathematically add 2 binary numbers together and the result is 256 or higher, it structurally requires a 9th bit. The physical 8-bit register cannot store this 9th bit, causing an overflow error. Much better, right? You're sounding like a computer scientist. But we need step 3 to get the A-star, the exam explanation. This is aggressively shaped for time pressure, and it is perfectly aligned with what we call the PEAL framework. Have you heard of this? Point, evidence, explanation, link. Top students structure their answers perfectly using PEAL. Point, you state the core concept. Evidence and explanation, you give the technical, step-by-step mechanism of how it works. Link, you aggressively connect it back to the specific context of the question. Students so often think they truly know a topic just because they mastered layer 1 or 2. But true exam mastery requires explicitly shaping that idea into the crucial 3rd layer to actually score those marks. This brings us beautifully into section 3, description versus explanation. Understanding this specific theoretical boundary is very often what separates a solid B grade from a top-tier A-star. Let's break this down. Description simply tells the examiner what the device, process, or method actually is. Explanation, on the other hand, tells the examiner exactly how it works and, critically, why it matters in the given scenario. And here's the kicker. Examiners usually expect both. If you only describe something, your answer sounds safe, but it's incredibly shallow. Out of a 4-mark question, you'll probably get maybe 1 mark. But if you try to jump straight into the explanation without clearly naming and describing the concept first, your response sounds confused, rushed, and totally incomplete. Let's do another interactive workshop right now to cement this. Challenge 2, speed writing. I am putting a 30-second timer on the clock for you. If an exam asks you to explain binary overflow, your description is simply defining it. You'd quickly write, an error that occurs when a binary result is too large to fit in the allocated storage space. But your explanation must tell me the how and the why. How does it work? When two 8-bit numbers are mathematically added, carrying over a 1 into a non-existent ninth column causes the system to drop the most significant bit. Okay, but why does it matter? This results in the computer holding a completely incorrect value, which can directly cause the program to crash. You absolutely need both sides of the coin to get full marks. Now, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Let's drill down even further on this absolutely crucial rule of sequence. You must explain the mechanism first, and then you state the consequence. In exam writing, clarity of sequence is quite literally everything. Computer science as a subject is largely process-based. You are dealing with algorithms, logic circuits, and step-by-step data execution pipelines. If you jump backwards and forwards in a process while you are writing, you completely break the logical flow that the examiners are desperately searching for in your answer. Think about our rushing student, Sam, again. Sam writes, the program crashes because of an overflow, which is when the 9th bit gets lost when you add binary. That logic is totally backwards. The examiner has to mentally reconstruct Sam's logic to give him marks, and frankly, they don't have the time or patience for that. Instead, follow the rule. Mechanism first. Adding two 8-bit binary numbers can produce a 9-bit result. The hardware register can only hold 8 bits, so the 9th bit is discarded. Consequence second. As a result, the stored data is entirely incorrect, which can cause the program to crash or output faulty information. Do you see how beautifully that flows? It is a tightly connected digital problem-solving sequence. It proves to the examiner that you truly understand the chain of events. All right, transitioning to Section 4, the power of context. This is the stage of our paleontological dig where we connect these highly abstract concepts to the real world. Because Cambridge doesn't just want theory in a vacuum, they want applied knowledge. Take a really close look at this list of real-world contexts on the screen. Mobile phones, websites and databases, automated industrial systems, robotics. You need to know that generic textbook responses rarely gain full marks on a scenario-based application question. If the exam paper sets a specific scenario, let's say an automated industrial system regulating pressure in a chemical tank, your answer must stay locked inside that specific industrial environment. Let's do Challenge 3, Data Scan. Imagine an exam question gives you a complex data table of water pressure levels inside an industrial pipe. I'm putting 60 seconds on the clock for you to think this through. The system uses an 8-bit sensor. As the physical water pressure goes up, the binary value goes up. What happens if the pressure forces the sensor to read a denary value of 256? Well, in an 8-bit system, we know 255 is the absolute maximum. That's 8 ones in binary. If it adds one more to reach 256, it rolls over to 8 zeros. It overflows. Now, if you just write on your paper the 9th bit is lost, you are only going to get partial marks. But if you apply the Peel framework in the context, you write, the 8-bit sensor overflows, causing it to transmit a binary value of 0 to the automated industrial system. The system falsely believes the pressure is completely 0, potentially causing the pipe to physically burst because it won't trigger the safety release valve. Do you see the incredible difference there? You are converting dry theory into a high-stakes real-world consequence. That is how you secure full marks. And this quote right here perfectly captures exactly why we do this. Real-world transfer matters because it converts memory into usefulness. When you repeatedly practice connecting abstract topics like binary overflow to familiar, everyday technology during your revision, you end up remembering not just the label, but the exact fundamental reason the concept exists in computer science at all. It stops being a boring textbook definition to memorize, and it actually becomes a vital, fascinating piece of engineering knowledge. You aren't just memorizing anymore, you are actually understanding. And trust me, the examiners marking your paper can always spot the difference between a student who merely remembers and a student who truly understands. And that brings us to Section 5, the 4-question mastery check. This is your ultimate final self-check to ensure your extracted fossil of knowledge is completely intact, cleaned up, and 100% ready before you walk into the exam hall. If you can sit at your desk and answer these 4 prompts aloud without looking at your notes, the topic is ready for the exam. Let's run binary overflow through this mastery check right now. Number 1, what is it? It's a critical computational error occurring when data exceeds the physical storage capacity of a register. Number 2, how does it work? When adding 2 binary numbers, if the sum requires more bits than the system architecture supports, like requiring a 9th bit in an 8-bit register, the most significant bit is lost. Number 3, where is it used? Well, it affects any digital system with fixed register sizes, like a robotic arm calculating its rotational degrees on a factory floor. Number 4, why is it worse than an alternative? Unlike a standard error message that deliberately stops a program safely, an unhandled overflow might just silently store the wrong number, causing that heavy robotic arm to swing wildly out of control instead of just shutting down. Boom! That right there is 100% complete, high-level, Cambridge-ready understanding. You've successfully hit the description, the explanation, the sequence, and the context. You are fully utilizing the PL framework. You are officially no longer a bulldozer. So the crucial takeaway point is this. Topics like binary addition and overflow are not just isolated vocabulary lists to be memorized. They are connected, digital problem-solving sequences that solve highly specific data handling issues. And here's the secret. Whether we are dealing with memory versus storage, a compiler versus an interpreter, or simple binary maths, the foundational rules of how you explain them to the examiner remain the exact same. This is your computer science success blueprint. Rule 1, you meticulously decode the command word. Rule 2, you fully apply the PL framework, stating the mechanism first and the consequence second, locked into the examiner's context. And Rule 3, you apply the time management matrix, knowing that a structured PL answer actually saves you time because you aren't rambling. You get in, you score the marks, you move on. To wrap this all up, I want to end with this provocative challenge for you to try on your own. Use a realistic computer science scenario to justify the use of binary addition and overflow. Why does it critically matter? I want you to actively apply your new paleontologist skills to this question right now. Think about an airplane altimeter tracking altitude, or a banking app calculating compound interest. Work carefully through those 3 layers. Keep digging, stay incredibly focused, and remember, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Also, drop a comment below with your exact target grade for computer science and the absolutely biggest challenge you're currently facing. Our team reads and responds to every single comment. Like and share this video with a study partner who needs to stop being a bulldozer. Ace the Exams. Your Cambridge success starts here. I will see you in the next explainer.